So, as promised, give you guys a run through of just the types of questions to expect, right? So that you aren't blindsided when you get into the test on Tuesday. So test number 1 is on Tuesday. Just for the first 50 minutes of class. First 50 minutes for the test. Then section 2.6. Well, we'll see how far into 2.5 I can get today, and then obviously wrap up 2.5, and then. But remember, 2.5 isn't on the test, so that's why I'm kind of. We're supposed to start it, but focus on 2.3, which is actually on the test. So the first question. And these guidelines will be pretty vague, but given f of x, evaluate, oops, that should say evaluate f at a plus h minus f at a over h. So if I give you any function, are you able to kind of balloon this thing out, right? Evaluate it, simplify it. Remember, the goal is that h in the denominator is usually going to cancel, or it will cancel, right? And so if it doesn't cancel, you did it wrong. Right? So it's just question 1. I'd say that's chapter 1 stuff, right? Just kind of being comfortable with functions. Question 2 is, given a function, part A, you have to state the domain. Right. Part B, remember how we used that sign chart last day to show that the where the limits are, or where the vertical asymptotes are? Right, so we use limits, sorry, to see which way the vertical asymptotes were going. Right? And so use a sign chart with limits to show there is a vertical asymptote. To show there is a vertical asymptote. And we did one just like that last day. Question 3. Given a function, this function is going to be a piecewise defined function. Just a heads up, a piecewise defined function. The first part of this is going to be to sketch the graph of this function. Now, this is not going to be a hard function to sketch. Okay, it's going to be, you know, a line, maybe a parabola in there, right? And so as long as you kind of know what a straight line looks like, what a parabola might look like, right, then you can just pick points of x, evaluate that function at those points, right? Plot those points, connect the dots, right? And so it's not going to be a hard function to sketch. Okay, and the reason you want to have that function, or the sketch, rather, we've seen it's way easier to figure out what limits are if we've got the sketch of the graph, right? Or if we know what the graph, bless you, if we know what the graph looks like, it's easier to figure out what the limits are, right? And so sketch the graph. Sketch the graph. and then find limits, right? Using that graph, of course. For sketching that graph, right, to plot a straight line, you only need 2 points on that curve, right? So you need to figure out 2 values of x, evaluate the line at those 2 points, figure out where they are, connect the dots, right? And if you've got some sort of parabola shape, right, up or down, pick maybe 2 or 3 points of x, figure out where they map onto the graph, right? Connect the dots, and you're done. So you could do it. Also, if we've got the graph, this is kind of a gimme mark, you can figure out where it's increasing or decreasing, right? If it's increasing, then you've got this kind of upward direction, right? If it's decreasing, then it's downward, right? And so where is it increasing or decreasing? Okay. Question 4 is going to be, it has parts A to C, and it's going to be limits. Okay. So just those limits, or at least the types of limits that we've talked about, right? Usually we look at this limit and we say, oh, well, if I put in the x that I want, right? I'm going to end up dividing by 0, for example. So then we said, oh, well, I can actually rearrange this so that I'm not dividing by 0 anymore, right? So those tricks. So go back and have a look at the tricks that we went through. I'll do another one today with absolute value, right? Just to kind of see how those behave, right? Because they're not going to be limits where you can just plug in the value of A and just go for it, because it's not going to work. Question 5 is the only one that we haven't covered quite yet, but we'll almost start with today, is on the squeeze theorem, which is pretty fun. The squeeze theorem, give you a heads up, is just if you know the limit of this function and you know the limit of this function, then a function between those two, well, if these two limits are the same, then that function in the middle has to have the same limit as the other two functions, right? So it's being squeezed by the other limits. So that's what we'll talk about today. And the squeeze theorem is actually, I don't know, kind of fun. So any questions about test 1? Remember, it's only 10% of your grade. We've got 3 more tests after this. So it's not something you have to worry about. Just get excited for. All right. Great. I'll start a new page here. How about if we did an example, and this is example 8, but I wanted to show you guys this one. So prove that the limit as x goes to 0 of the absolute value of x over x does not exist. So now I'm telling you it doesn't exist, but you're going to tell me why, right? How we approach this, right? If you think about what we said last day was, well, for a limit to exist, right, the left-hand limit has to equal the right-hand limit. If they don't equal each other, then the limit does not exist, right? That's one way that the limit cannot exist. So the absolute value, oh yeah. Oh, that's my sloppy limit. Yeah, LIM. I'll try to clean it up, but it's going to look about the same. That one's better though. So the limit as x goes to 0 of the absolute value of x over x, well, if we just plug in 0 here, right, we'd have 0 over 0. We can't divide by 0, so we have to find another way, right? And so we look and say, well, I know how the absolute value of x behaves, right? If x is positive, then the absolute value of x is just x, right? If x is negative, right, then the absolute value is going to be negative x, right? Because if x is -2, for example, the absolute value makes it positive, but how we do that mathematically is we take -2, right? And so, so we know that the absolute value of x equals x when x is greater than 0. And we also know that the absolute value of x is negative x when x is less than 0. Whoops. And we're not talking about at 0. We could, it'd be in the top one, but. So what we can do, right, if we're approaching x equals 0, then we're going to be coming from x is the negative side up to 0, right? From the left, all those x's are negative. From the right, all those x's are positive, right? And so what we can say is that the limit as x approaches 0 from the right, right, which we denote by a little plus superscript, of the absolute value of x over x is the limit as x approaches 0 from the right of just, so now, right, from the right, approaching 0, all those values are going to be positive, and so we know that we're safe to just replace the absolute value of x with just x, right? Over x. So this one is the one that's backing that up. X over x, just 1. Right? The limit of a constant is just that constant. So now we have the limit as x approaches 0 from the right of 1 is just 1. Now, if we approach it from the left, right, now all our x's are going to be negative. So now, if we look at the limit as x approaches 0 from the left of the absolute value of x over x, we have the limit as x approaches 0 from the left of negative x over x. And that's because here, that's what we said. So you have to think about, well, how is x behaving? As I'm approaching 0, right, is it going to be positive or negative? Okay. This is going to be the limit as x approaches 0 from the left of -1, right? Negative x over x is -1. And so I get -1. This tells us that the left-hand limit does not equal the right-hand limit, so it doesn't exist. Right, which was what we were trying to show, right? Prove that this does not exist. So, since the left-hand limit does not equal the right-hand limit, oops. We can say the limit does not exist. Right, that's what we established last day. in order for the limit to exist, the left-hand limit has to equal the right-hand limit. And just to save us a little bit of writing here, what if we just abbreviate the left-hand limit to LHL and the right-hand limit to RHL? And then we can just say, or we could even drop the HL and just say L does not equal R, if you want to go that route, right? Because we are going to be using this argument a lot, right? Oh, the limit doesn't exist because the left-hand limit does not equal the right-hand limit. Or the limit does exist because the limits are equal, right? The left-hand limit equals the right-hand limit. So whichever one. This applies for any absolute value over the thing that's inside the absolute value, right? So even if we looked at something like the limit as x approaches, is due to, hang on. Where does it tell me the, I feel like there was a message, but no. I don't know where it went. Sorry, summary. I don't know. I lost it. Unless you guys saw the message. Something about positive and negative. Yeah. So if we've got, so I'm just going to make something up, right? Something big. So the limit of the absolute value, right, of x squared minus 4x plus c, as long as it's over x squared minus 4x plus c or something kind of that's the same, we can use the same argument, right? I'm not sure whatever would make the value in the denominator 0 is what I would ask you to take the limit to, right? So as long as you recognize that, okay, if I've got the absolute value of blah, as long as it's over blah, I know the limit doesn't exist, right? Because I can use that same argument, but I can break up the absolute value for when it's positive and for when it's negative. Okay, so I'm going to remove that because it's not complete, but just so you get the idea. Okay. Any questions about that one?
The one you just did, like, doesn't exist, right?
Yeah. Mm-hmm. Yeah, so you could break it up and use that same argument, right? The positive version is going to go to 1, and the negative version is going to go to -1. So they'll never meet. So if we have piecewise functions, we can look at their limits as well. And so if we let f of x be a piecewise function of the square root of x minus 4 and 8 minus 2x, the square root of x minus 4 if x is greater than 4, and 8 minus 2x if x is less than 4. Does the limit as x goes to 4 of f of x exist? We established that the function doesn't necessarily need to exist at 4 in order for the limit to exist, right? The limit, as long as the function's approaching the same point, right, or the same limit from the left and from the right, then we can say that the limit exists, right? Even if there's a little discontinuity in there, right? A little hole in there, that's fine. right? So here, what we want to do is, well, if x is greater than 4, then that's going to be my, where I'm coming from the right, coming up to 4. And then if x is less than 4, then that's where I'm going to be coming from the left, if x is less than 4. Okay. So we want the limit as x goes to 4 from the left. Right. I guess you could do right because it's from the right and then the left, doesn't matter. The limit as x goes to 4 from the left of f of x is the limit as x goes to 4 from the left of 8 minus 2x. There's no reason that I can't just plug in x equals 4 in here, right? For any polynomial we said, or even a polynomial divided by a polynomial, we're allowed to just plug in the value as long as that value is in the domain, right? And so 8 minus 2x, you can plug in anything. There's no illegal math here. And so 8 minus 2 times 4 puts me at 0. So now, in order for this limit to exist, the limit as I come in from the right also has to equal 0, right? If it doesn't, the limit does not exist. So then the limit as x goes to 4 from the right of f of x is the limit as x approaches 4 from the right of the square root of x minus 4. I'm coming in from the right, onto 4, so the smallest value that I could plug in here is 4, right? I need to be careful that I'm not taking the square root of a negative number, but I wouldn't be because the smallest possible value that I'm going to reach is 4. 4 minus 4 is 0. I can take the square root of 0, right? And so here, if I plug in 4 into this value because it's in the domain now, well, I get the square root of 4 minus 4 is 0. Oh, that wasn't very good. I always have a hard time with my curly brackets on the right. My left-hand curly brackets are usually pretty nice. Since the left-hand limit equals the right-hand limit, we can say that the limit as x goes to 4, just in general, of f of x exists and it equals 0. You could try graphing this thing. This piecewise function wouldn't be unreasonable to ask you how to graph it. Right? Knowing how root x behaves, right? Helps. That's why we went through that catalog of functions in chapter 1, just so we kind of have an idea of what things are going to look like. But as long as you know that if x is less than 4, x is less than 4. Oh yeah, if x is greater than 4, sorry, I mixed them up. If x is greater than 4, then you've got this square root function, right? If x is less than 4, then you've got this straight line, right? And so we can say, okay, well, if I've got something like this going on, I know from the limit, right? I know that the y value at x equals 4 must be 0. So I already know that here, let's call it at 4. I've got this open hole here. Okay. It's an open hole, right? Because it's not defined at x equals 4, right? So the limit is 4, or the limit is 0, sorry, at 4. but it doesn't have to exist at 4, the function. And if x is less than 4, then I've got this straight line 8 minus 2x. So if I plug in x equals 0, for example, just for a convenient other point, remember to graph a straight line, you only need 2 points. Looks like I already have a point on this line, right? And so I need another value of x. Let's plug in x equals 0. Then I get 8 minus 0. Let's put it somewhere up here. So then, oops, there, got weird. So this is 8 minus 2x. Now it does help to know what the square root of x looks like, right? The graph, kind of this bow shape. And so if I've got x is greater than 4, what if I plug in x is 5, right? Then I get 1, because I get 5 minus 4, the square root of 1 is 1. And so here at 5, I'm at, let's say this is 1. Anyways, my scale is a little weird, but it might look something like this. On the test, you'll have the grid, so it'll look a little bit nicer and be a little bit easier. Here we're just sketching. Yeah, I just didn't draw it very well. I'll move my point, how about there? Right, because now it's defined for all these values, and so it's going to keep on going and going, and so this can be the root of x minus 4. And you can always plug in more values of x if you're not sure what it's going to look like. Right. Cool. All right. I've been ranting and raving about the squeeze theorem. Let's do it. The squeeze theorem. Oops. Which, like I said, is that the last question on your test on Tuesday. But once you kind of get the hang of it, it's pretty fun. If f of x is less than or equal to g of x, which is less than or equal to h of x, essentially, if g of x is between f and h of x, right? When x is near x equals a, except, just like we saw in the previous example, except possibly at x equals a, right? The limits don't care about the actual value unless the actual value just happens to be on the line, right, of the function. Except possibly at x equals a. And the limit as x goes to a of f of x, we're told is L, or we can find it, and it is some limit L. And the limit as x goes to a, right, so going to the same point of a, of h of x is also L. So now I'm saying that g is this function that at a, it's being captured by f of x and h of x, both of which have a limit of L. Well, the squeeze theorem says that, well, g of x must also have a limit of L, right? It can't, it's bounded by f and h, so it can't run away. Then the limit as x approaches a of g of x must be L. This is the squeeze theorem. I think you can call it like the pigeonhole theorem, and it's got all kinds of weird names, but they'll all make you think of like, oh, squeezing through a little crack or something. So if you imagine, if you've got some XY axis, and let's put, I don't know, here's f of x, and then here, let's see here. I have to draw it carefully this time because it has to go and squeeze. That's h of x at some value as x approaches a. Then if we've got some function that kind of looks like whoop, whoop, let's call it g of x. It's squeezed between f and h, and so it has to have the same limit, L. Because here, that's at L. Usually it is an oscillating function. Think of sine and cosine, for example, right? So most often it's going to be sine and cosine. That's going to be squeezed between two other functions that we know how they behave, right? Which you'll see when we do our example. Okay. I'll summarize this. So the main use is to find the limit of an oscillating function with upper and lower bounds. For example, the limit as x goes to 0 of x squared sine 1 over x. As soon as you see the sine or cosine, right, you can probably think squeeze theorem, or at least try it, right? But usually it'll just say use the squeeze theorem to find this limit, right? And so just kind of pointing in the right direction. But we know how sine and cosine behave, right? We know that sine x, whatever is inside the sine, right? We know it oscillates between -1 and 1, right? And so knowing that about sine and cosine, right? So we know that sine theta, just any sine theta, is between -1 and 1. Okay. So therefore, sine of 1 over x is also between -1 and 1. And as long as we're not doing stuff to the outside of the sine, or I don't know, doing something weird, we're okay. So if we know that sine of 1 over x is between -1 and 1, right, then, well, I want x squared times sine 1 over x. Right? So what if I just multiply x squared all the way through, right? Then I would be able to say, because I can multiply all of these pieces by x squared and nothing would change, right? The inequality would remain the same. So then I'd have negative x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared, right? I'm allowed to do that. I'm allowed to take some value. As long as I multiply it to all of these things, the inequality will stay the same. And so we can multiply all parts of the inequality. Oh, sorry, I almost did root x squared by x squared. Why am I not worried about it changing the inequality? X squared is always positive, right? X squared is greater than or equal to 0, right? Because if I square a negative value, it just becomes positive, right? And so the inequalities are unaffected, right? Because if I'm multiplying or dividing by a negative, right, that's when I have to switch the sign, and so that's bad news for me, right? So we want to make sure that whatever I'm multiplying by can't switch the signs around without me knowing, right? So x squared is always positive, and so what we can do is we can say, okay, well then I have negative x squared is less than or equal to, oops, sorry, x squared. Oops. X squared sine 1 over x, which is less than or equal to positive x squared, right? Just multiplying through. This is the function that I want the limit of, right, in the middle. X squared sine 1 over x. I don't know exactly how to find that limit, but I can use the Squeeze theorem and say, well, I can find the limit of negative x squared as x goes to 0, right? And I can find the limit of x squared as x goes to 0. Right? You can probably tell that both of those are going to be 0, right? And so, well, if x squared sine 1 over x has to be between 0 and 0, well, the limit must be 0, right? And so if we take the limit as x goes to 0 of negative x squared is just going to be 0. And the limit as x goes to 0 of positive x squared is also going to be 0. Or I guess I could ironically squeeze them in. I wrote so lofty though, hang on. I can keep them in the, let's see, in the inequality, right? Not break them up. Make it be a little bit easier to see. The limit as x goes to 0 of negative x squared is less than or equal to the limit as x goes to 0 of x squared sine 1 over x, which is less than or equal to the limit as x goes to 0 of x squared. 0, So less than the limit as x goes to 0 of x squared sine 1 over x less than or equal to 0. Therefore, we must have the limit as x goes to 0 of x squared sine 1 over x equals 0. So what you're going to do, right, is you're going to figure out, okay, well, there's going to be a sine or a cosine in there, right? And so you'll start with just the bare bones sine and cosine, right? Sine and cosine, that's going to be between -1 and 1, right? And then you're going to multiply or, you know, add or subtract or do whatever you need to do to everything in the inequality to make the center look like the function that you want, right? So do what you have to do to get the middle part to look like the one you're interested in. What you'll find is that the outside portions should be pretty easy to find the limits of, right? And then those limits should be the same if it says to use the squeeze theorem, right? And then you can just say by the squeeze theorem, right? I know what the limit is. And in this case, it's 0. Let's see here. Any questions about that one? No. All right. Okay. So that's where the test is going to. Right. I know we still have to talk about material that's not on this test, but it is on the next test. So let's start a new page here. Section 2.5 is on continuity. We've already kind of touched on continuity, right? If a function is continuous, like a polynomial, for example, that means that we're able to just figure out what the function is at a if we're finding the limit as x approaches a, and we can just plug in that value, solve it, easy, right? Or even if we have to rearrange some stuff, right, then the limit becomes quite a bit easier. So a function f of x is continuous at a number a. Oops. If the limit as x approaches a of f of x is equal to f of a, right? So essentially, if we're able to just plug in a into our function and it gives us a limit that exists, then it's continuous, right? So we can argue it that way. Or if we have a function, just deciding if I should draw a box around this or no, I'll make a big box later. There are actually 3 things that are required for a continuity at x equals a. So 3 things required for a continuity or I guess I should just for continuity. Continuity at x equals a. The first one is going to be that the limit exists. Right? And so the limit as x approaches a of f of x exists. You can check this, right, by checking that the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, right? That's how we know a limit exists, is because the left-hand limit equals the right-hand limit. The second thing, well, a has to be in the domain of f. So a is in the domain of f. Right. So f of a must be defined. Is defined. So f of a is defined. And then the third point is that the limit has to equal f of a. So the limit is equal to f of a. Which is what we said earlier, right? We said, well, in general, it's going to be continuous if the limit as x approaches a of f of x equals f of a. If it equals f of a, it exists, right? F of x must be defined at a because we're able to evaluate f of a and get some number, right? And so then the limit must be f of a, right? And so a continuous function is going to just look like, if you have y equals f of x here, at x equals a, a continuous function, you can think of it as any function where you can just draw it and it's just a straight line, or sorry, not a straight line, a line that just continues, right? So you can draw it without lifting your pencil from the page, right? So there's no discontinuities, there's no asymptotes, there's nothing going on, right? And so here, let me see here. So at a f of a, that says f of a, it's really small though. There. Still small. Right. So if it's continuous, then yeah, the limit exists at that point, and the function exists at that point, right? It's defined at that point, and of course that limit has to equal f of a. Because remember before we had that example of, well, we're allowed to have something, just kind of sketching here. We're allowed to have something with an empty hole here, and then it's defined up here. The limit of that still exists, and it's going to be just on that curve still, right? It doesn't care about where it's actually defined, but that's not continuous, right? And so we'll talk about all the different discontinuities, but for now, focus on being continuous. All right. If one of these three doesn't hold, right, then we have a discontinuity at a. If one of these three requirements are not met, f of x has a discontinuity at x equals a. This, I'm going to draw a box around all of this. It's helping us figure out if a function is continuous or not. I'll start on a new page here. An example. Let's see if I can draw this out again here. So we've got x, we've got some y, and we're just going to look at all the different types of discontinuities, right? Because there's different types of discontinuity. So if we've got some curve here, so at some point A1, there's a hole there. At A2, it stops, but it's inclusive. And so if I start right above A2, kind of go have open circles on both ends. Doesn't really matter how you draw the lines in between in this case. They don't really do anything. But now I've got, so f of A3 is defined, right? But it's up above the line. And this is going to keep going here. And just kind of imagine all the people like this. A4. There. Okay. Something like this. So we've got little points of interest here, A1, 2, 3, and 4. We're going to look at all these different types of continuities. We can see, right, that all of these are discontinuities, right? I've got a hole at A1. I've got a jump at A2. At A3, I've got another hole, even though it's being filled, but it's not defined, right? It's not continuous on that curve. And then at A4, I've got another discontinuity, right? I've got this asymptote. So we can see that all of these are discontinuities. That's not the problem. But let's just talk about why they're discontinuities. And so at the points A1, let's start there. The first condition was that the limit exists. There's no reason to say it doesn't, right? If I approach A1 from both sides, the limit exists, right? And so that's good. But f of a is not defined, or f of A1 is not defined. So at A1, the limit exists, right? But f at a1 is not defined. Right. We call this a removable discontinuity. The reason we call it removable is because we could easily remove this discontinuity, right? It doesn't need to be there by just connecting the line, right? And so we call it a removable discontinuity. This is a removable discontinuity. At A2, right, well, the limit does not exist, right? Because the left-hand limit does not equal the right-hand limit at A2. And so, well, that's out. The limit does not exist. Does not exist. So we end there. This is called a jump discontinuity, right? Because we've got this kind of jump going on here, right? So it makes sense. This is called the jump discontinuity. If we move on to A3, right? Looks like the limit exists, right? F of A3 is defined, right? But the limit does not equal f of a, right? And so it's a discontinuity. So at A3, the limit exists, and and f of A3, hey, keeps erasing my stuff. F of A3 is defined, but the limit as x approaches A3 of f of x does not equal f of A3. This is another removable discontinuity because all I would have to do is bring that point down onto the line, right? And there's no reason that says it has to be up there. Right? It's all part of the domain, it's just not in there. And so this is another removable discontinuity. And then here, right, well, we can start with the limit does not exist, the function's not defined at A4, and therefore the limit can't equal f of A4, right? And so none of the conditions are met, right? For A4, right, the limit does not exist. F at A4 is undefined. So of course that limit, because it doesn't exist, right? I'm not going to say the limit does not equal f of A4 because it doesn't equal anything. We usually specify that this is an infinite discontinuity. Even though it is kind of a jump discontinuity too, but jumps. So it is a jump, but we usually specify that it's an infinite discontinuity, right? Because it looks different than the actual jump discontinuity. Okay. Let's do another example. Find all discontinuities, if any. Find all discontinuities if there are any. F of x is going to be piecewise defined, and it's going to be x squared minus x minus 2 over x minus 2 if x is not equal to 2. And it's going to be 1 if x equals 2. I'll give you guys some time to work on that one for a little bit here, and I'll pause this recording. Hopefully I'll remember to. So if you have to find discontinuities, right? Well, the first thing we're going to look at is, well, is f of x defined everywhere, right? Regardless of if there's discontinuities or anything like that. What's going on in f of x? From the top function, right, we can say that, well, I already know that x can't be 2, right? 2 minus 2 makes us divide by 0, but that's taken care of, and that's why we have this piecewise function. So it looks like f of x is defined everywhere, right? And so we see that the domain of f, of x is the set of real numbers, right, from negative infinity to positive infinity. Yeah. So the problem is not that we've got any loops in our domain, right? But we want to know, okay, but we've still got this glitch at x equals 2, right? And so we want to know, the only problem is going to be if x isn't equal to 2, then I can find the limit of f of x at a, right? And so if if x is not equal to 2, if x is not equal to 2, we can find the limit as x approaches, let's just call it a, of f of x. Well, if it's approaching a, delete this, and it's not equal to 2, right, then I can just plug in, there's no reason to say that a minus 2 is going to be 0, right, because it just can't be 2. Right? And so then we can just say that it's going to be a squared minus a minus 2 over a minus 2, right, whatever that is. Okay. And so that's not really the problem. Right? So the limit exists at x not equal to 2. Okay. But is it continuous at x equal to 2? But is it continuous at x equal to 2? Well, so we can find the limit everywhere else. It's just this little x equals 2 that's holding us up, right? So that's the point that we're going to check. So the first thing we're going to check, right, is, well, if x equals 2, I want to find that the limit exists, right? The first checkpoint, the limit has to exist. The second checkpoint, it has to be defined, right? And the third checkpoint, the limit has to equal f of a, right? And so those two have to equal each other. And so the first thing we have to check is we have to find the limit as x approaches 2 of f of x, which is the limit as x approaches 2 of x squared minus x minus 2, I want to say, over x minus 2. This is one of those limits I was talking about, right? Where, yeah, if we just plug them in, we're going to divide by 0. That's bad news, right? But we can rearrange some stuff, right? The x minus 2 in the denominator is the one that's kind of holding us up here. And so we're going to do whatever we can to try to cancel it, right? And so we can factor the x squared minus x minus 2 into something that hopefully has an x minus 2 in it, so that we can cancel it, right? And so you're always on the lookout for something. If you see something like this, then you want to try to factor your top so that it has an x minus 2 in it, right? In this case, so that they can cancel. And in fact, if we rewrite this as the limit as x approaches 2 of x plus 1 times x minus 2, turns out that works out. Over x minus 2. Because now we've dealt with that. Now I'm just at a simple polynomial here, so the limit as x approaches 2 of x plus 1, well, that's just going to be 2 plus 1, which is 3. So therefore, the limit exists the limit exists now our second checkpoint, right, is, well, f at 2 we know equals 1, right? So f at a in general, therefore f of a is defined The problem, though, that we can already see is that, well, the limit is 3 and the function is 1, right? So the limit does not equal the function at that point. So we have this discontinuity. So the third one, squeeze it in on same page. The limit as x approaches 2 of f of x is not equal to f evaluated at 2. So because if we kind of visualize it, right, knowing that the limit exists, that means that we've got curves coming up to some point, and then knowing that the function is also defined, but somewhere else, right, if we had to visualize it, then this would be a removable discontinuity, because we could just kind of plop it down, right? Can't because it's not in the domain, but we call this a removable discontinuity. Any questions about that one? No. Okay. Just like we started with overall limits, and then we went to left-hand limits, right-hand limits, and then they have to be equal to each other, right? limits can be continuous from just one side, right? So everything can be hunky-dory coming from the left, for example, but then everything else is just kind of weird, right? So limits can be continuous from one side. Which looks like if it's continuous from the left, then the limit as x approaches a from the left, sorry, not -1, from the left of f of x equals f of a. Right. So even if you're just able to boil it down to one of the side, right, one of the sides, you could at least say, well, it's continuous from the left or continuous from the right, right? If we're coming in, so continuous from the right means that the limit, it's like my imaginary pen is running out of ink. Keeps doing like really light lines and then heavy. I don't know what is going on, but I'm gonna try to clean it up here. Yeah, is that what it is? Oh, hey, I didn't know I could do that. Cool. That might be what's going on here. 17, I don't know. Feels disappointing. 17, it should be doing all right still. So if we take, so that's the limit as x approaches a from the right of f of x can be written as f of a. Which is the same definition that we started with, right? If the limit as x approaches a of f of x is f of a, right, then we can say it's continuous, right? If you're able to make that, pardon the pun, the jump, right, to saying that, well, the limit is the same as the function at that point, it's continuous, right? Usually we go the other way around and say, and argue that because it's continuous, I'm able to evaluate it just at that point, but it depends. Remember how we kind of talked about the sine and cosine, the inverses and stuff like that, and how we restricted the domain that we were interested in, right? We could say that, well, this function, it's not continuous forever, but it is continuous on this interval, right? And so that might be of interest as well. And so continuous over an interval, oops, we say that f of x is continuous over an interval capital I, which is usually what we use to denote just some random interval capital I, then f of x is continuous at every number a in the interval I. So then f of x is continuous at every number a in the interval I. Can draw a little box around here. So for example, if you have f of x is equal to root x, right, this is going to be continuous starting at 0, right? It doesn't exist for x is less than 0, right? And so here, this is continuous on the interval 0 to infinity. So it's not continuous always, but it is continuous on this interval. So more theorems, more rules, more laws. This next one kind of, it's hard to tell what the difference is between this next one and those limit laws that we established earlier, right? So I think maybe 2 days ago, maybe it was last week, maybe it was earlier this week, I can't remember, right? But essentially what we said was, well, I can bring that limit inside, right? If I'm taking the limit of two functions being added together, I can bring it inside, right? And so here we're just going to say that again, right? But just say it in terms of just the functions instead of the limits on the outsides. But it is the same, so don't be thrown off. I guess it's just specifying that f and g have to be continuous for this to work. So let f and g be continuous at a. Let lowercase c be a constant. Then the following are all continuous at a. Thinking about what it means to be continuous, well, if I know that f and g are continuous, right, then that means that the limit of f equals f of a, right? The limit of g is g of a, right? And so it's not that weird to say that f plus g must also be continuous, right? Because like I said, I can split that limit onto adding the functions. And so if f is continuous and g is continuous, adding the two, yeah, I get a continuous function, right? And so it's not that crazy. F minus g, same thing. C times f, right? A continuous function multiplied by some constant, still constant is still continuous. F times g, right, multiply two continuous functions, still continuous, and then f over g, as long as g is not equal to 0. So it's not that bizarro, right? If we think about those limit laws, right, and knowing that f is continuous and g is continuous, yeah. I guess it is a theorem, so I'll throw a pink box around it, but there's a list of functions that are always going to be continuous, but the holdup is that for all the values in their domain, right? And so some of them might have domains that don't, or values of x that aren't in the domain. And so the following functions are continuous at every number in their domains. That's really important, right? We can't just stop at every number in their domains. Not that helpful, but if we're kind of familiar with the domains of these things, then yeah. First one we already talked about is a polynomial, right? So polynomials are continuous, and that's why we're able to just plug in a into that value. Yeah, I'll just got the list here, so I better not jump around too much. Logarithmic functions. You know what? It's understood that all these are functions, so I'm not going to write it for, got it on some of them and not on the, right? Logarithmic functions, exponential functions. Radicals. Rational functions or rational. Trig functions. Trigonometric. And inverse trig functions. Right. Especially some of these trig functions and inverse trig functions we've already talked about, while their domains might not be all real numbers, right? Especially thinking about tan, for example. Right? We know that there's these asymptotes going on, right, at regular intervals. And so those asymptotes are obviously not in the domain of tan, but it is continuous everywhere else, right? And so that's what this thing is saying, that, okay, well, if you know where what the domains are, then we're able to determine where these things are going to be continuous. Right? Polynomials, right? A polynomial over a polynomial, then you can't divide by 0, but everywhere else. And so that's what we've kind of dealt with, where we said, well, I'm going to try to factor things out or try to get it so that I can just plug in a value, and that value is in the domain of that function. So, wait. Where, so as an example, where is f of x equal to the ln, so I'll write it nicer, try to at least, the log of x, the natural log of x plus tan inverse or arctan of x over x squared minus 1. Where is it continuous? To figure out what the domain of this thing is, right, we need to dismantle it, right? You've got a function plus a function over another function. So you can look at those domains individually and then the combined domain, right, is where they all overlap. So I'll let you work on that for just a little bit. And I'll do this again. So like I said, we're going to break this up into different components, right? And then try to construct the domain that way. And so if we look at, oops, sorry, that was not what I meant to do. The natural log of x, right, is continuous on 0 to infinity, right? Because, well, 1, it's a log function, so I know it's on the list, right? So now I just need to figure out, okay, well, it's continuous between 0 and infinity because that's the domain of the natural log of x, right? Or any log. And so then the inverse tan of x, remember that's that weird one? So sine and cosine went from having everything in their domain, right, to having a very restricted domain. And then tan went from having this kind of restricted domain to having this everything domain, right? And so, because now it's just this kind of, right? And so the inverse tan, right, or arctan if you want, is continuous on negative infinity to infinity. Looking at x squared minus 1 as just its own thing, right? X squared minus 1 is continuous everywhere. Right? Can consider it a polynomial, right? It's an itty-bitty polynomial. Continuous everywhere. There's no reason x squared minus 1 on its own, there's no holdups on its domain, right? It happens to be in the divisor here, so that's the problem. So x squared minus 1 is continuous on negative infinity to infinity. Yes? Yeah, that's where we're the next stop. Good. So where you guys, yeah. And I was like, hey, there's one thing I've sort of absorbed here. Can't divide by 0. Good. That's good. So then f of x, right, the whole combined thing, says that f of x is not continuous is not continuous when x squared minus 1, yeah, equals 0. Careful here though, right? Because solving for x equals 1. If I take the square root here, right, then x equals plus minus 1, right? Because if I plug in negative 1 into x squared, right, I get 1. If I get 1 squared is 1, right? So both of those are options. So those we need to keep an eye out for. Yeah. So it's not continuous when x is plus minus 1. The minus 1 isn't actually going to be a problem because we need to figure out, okay, now we need to overlap all of these restrictions, right? From 0 to infinity. So already we're only looking between 0 and infinity, right? So for the next one, 0 to infinity, 0 to infinity, right? Those are all the same. And then now we have to pull out when x is equal to 1, because between 0 and infinity, we're only concerned about the 1. And so what we have, if we kind of sketch it on a number line, is between 0, we know we've got a hole at 1, or I'll draw it up above a little bit. Oops. A hole at 1. Not including 0. Didn't need to be such a big circle. Therefore, f of x is continuous on, if we had to write this in interval notation, right, 0 to 1, not inclusive. I guess you could say exclusive. And then pick it up again at 1 to infinity. Let's do one last example. Yeah.
Is it break that one?
No, it's exclusive. Yeah, so it's pulled out. I'll make it nicer though. How about? Oh. Picky, but wrong color. There. Can't have the wrong color. When you're going back and looking through these notes, why was it a different color? Had to be there, I guess. Yeah, let's do a last example. And then we'll be all set for continuity here. So it's kind of a reverse engineering project here for this example. So for what values of C, is the following function continuous for all x. Our function is f of x is cx squared, and it's going to be a piecewise function. Cx squared plus 2x if x is less than 2. And it's going to be x to the power of 3 minus cx if x is greater than or equal to 2. So we know that the top function is continuous for all the values less than 2, right? And then the bottom function is continuous for all the values greater than 2, right? We just want to force these two to have the same limit and be evaluated to the same thing at 2, right? Because that's where they should meet, right? And they should be continuous, right? So we want it to be continuous over everything, right? So at 2, we have to kind of join these things up, right? So we already know f of x is continuous for x less than 2 and x greater than 2. But we need continuity at x equals 2. No. That means that the limit has to exist at 2, right, for both of these, and they have to be the same. So we're going to force them to be the same because we've got some wiggle room with choosing c, right? So we're going to force these c's to make the limits be the same, and also so that they have the same value at 2. And so the first thing we're going to do is find the limits. Looking at how we approach this, right, if x is less than 2, then we've got cx squared plus 2x, so I'm coming in from the left. And so the limit as x approaches 2 from the left of f of x is the limit as x approaches 2 from the left of cx squared plus 2x. This is just a polynomial, right? So I'm able to just plug in the values and go from there. So this is going to be the limit, or sorry, not the limit anymore, we're evaluating it. C times 2 squared plus 2 times 2. Which puts us at 4c plus 4. Now looking at the other function, right, the other side, the limit as x approaches 2 from the right of f of x is the limit as x approaches 2 from the right of x to the power of 3 minus cx. Again, I've got a polynomial, so I'm safe to just plug in the 2. So then I get 2 to the power of 3 minus c times 2. So I get 8 minus 2c. We need the left-hand limit to equal the right-hand limit. Oops. Which means that we need 4c plus 4 to equal 8 minus 2c. Right? So we need to find the c that makes that happen. If we kind of switcheroo here, right, I get 4c plus 2c is 8 minus 4. So I get 6c is 4. So c must be 4 over 6. Can simplify it to 2 over 3. Okay. So now, f of x is x to the power of 3 minus c to the cx if x equals 2, right? So we only have to focus on that one part of the function because that's what it is when x equals 2, right? And so what we want is, for the second one, we know if x equals 2, f of x was x to the power of 3 minus 2c? Or sorry, x to the power of 3 minus cx. So now I've got x equals 2 and c equals 2 over 3. So f of 2 is 2 to the power of 3 minus c, which is 2 over 3 now, times 2. So now I have 8 minus 4 over 3. Which if I combine, I'm cheating. but I'm also running out of time. The limits, right? Now we need to make sure that the limits both equal 20/3, right? Because that's what they have to equal if they're continuous. And so the limit as x approaches 2 from the left is going to be of, where was it? Cx squared plus 2x. So the limit as x approaches 2 from the left of 2/3 times 2 squared plus 2, oops, 2 times 2, which we're allowed to just plug in that 2 there, and it equals blah, 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 20/3, kind of simplifying things here. Doing the same thing as x approaches 2 from the right, right? From the right, we said that it was x to the power of 3 minus cx, which is the limit as x approaches 2 from the right of 2 to the power of 3 minus 2/3 times 2, which is also going to be 20/3. Phew. That is what we wanted / needed, right? Because now the limits are the same and we can evaluate it and they equal the same thing. Any questions? Nice work, guys. See you guys next week. Test time. Bye, guys. I don't know where.